Hello guys! Now we have so many layer 2 technologies, right? And we can use a VLAN to avoid the broadcast domain, but there also a problem, a failure here. If we have one device or one link is broken, the network cannot work. So we want to improve the network, have higher ability. Maybe we can provide multiple device, multiple link, but in some scenarios there is a loop. So how to solve the loop and also want to get the higher bandwidth, higher redundancy, we can use the technology of the STP. So the first part, I will explain you about the detail why we use this technology. And the second one, about the STP, how to work, what's the principle to solve the loop. And the third one, I will also explain some basic configuration for you. And the fourth one, STP also has some advanced characteristic. What's the problem? What's the application scenario? If you are interested, let's see the detail together.
Hello guys, here is a detailed video of STP principle. The same process. Before we talk about the detail, let's have a review of the practice question about the VLAN. The first question is, which of the following are characteristic of a VLAN? The correct answer is A, B, C, and D. That means if you deploy the VLAN, you can make a logical-based grouping and which can be grouped across two series of functions, but not limit on the physical places. So this is option A and option B. And about option C, if we use a VLAN, we also can reduce the management costs associated with nodes movement in the network. Because if you use some physical device like the router, you have to make lots of router if you want to divide multiple layer 2 broadcast domain. And the third one, pay attention. Within the same VLAN, they can directly communicate with each other through layer 2. But if some communication between different VLANs, we need the layer 3 device, like the layer 3 router, like layer 3 switch and the router. And how to work. When we talk about the routing information, we will discuss it. How to make the communication between different VLANs. So the answer is option A, B, and C, and D. And about the second question, this is a topology, right? We have multiple VLAN and connect with two switches, and there are 5 hosts. And about the configuration of the switch, switch 1 and 2 connect with each other, we make the interface to become trunk. And about the different one is we make different native VLAN. About the switch 1, the interface, we will use the native VLAN 30. And about the switch 2, the native VLAN is 20. And about the interface to connect with PC 1, 2, 3, 4, and 5. All of them, the type is access interface, but the VLAN is VLAN 10, 20, and 30. So, if we add the configuration on the switch, which of the following hosts can communicate with each other? And communicate with each other means if I send the message to you and you also can give me the reply, that means communicate with each other. And the answer is option A and C. That means about the option A, PC1 and PC4, they belong to the same VLAN, right? VLAN 10, and they can communicate with each other. And about the option C, PC3 belong to VLAN 30 and PC5 belong to VLAN 20. They can communicate with each other. Maybe someone confused. Why is option C not about the option B, right? PC2 and PC5 both of them belong to VLAN 20. So let's see the detailed process. How do the communication with each other? First, let's see the communication between PC1 and PC4. It's very easy for us to understand. The first one, once the PC1 sends a message out, there is a standard Ethernet message. So there nothing information of the VLAN ID. And when switch 1 receives it, we will add the VLAN 10 because we already make the first interface to become access and the VLAN ID is VLAN 10. If we add the VLAN 10, then the message cannot be sent out through the second interface or the third interface because the VLAN ID is different. Then the message can be sent out through the link between two switches, so the message will directly send out. Of course, before switch 1 sends a message to switch 2, we will compare the native VLAN with the message VLAN ID. We will find the native VLAN is 30 is different with the message VLAN. So the message can carry the VLAN information and then pass through the link. When switch 2 receives it, I will check the VLAN ID. The VLAN ID is 10, so I will directly send the message to PC4 because the same VLAN ID of the first interface. So the message will be sent out and we will delete the VLAN ID of the VLAN 10 because about our terminal, we cannot recognize what means the VLAN ID. That's why we will use the access interface to connect with the terminal. So this is the communication from PC1 to PC4. It's correct, right? And then we analyze the communication from left to right, and the next step we will analyze the communication from right to left. And the next step about the PC2, if we send the message out, also this is a standard Ethernet message. And we will send the message to switch 1. Switch 1 will add the VLAN to become 20. And then the message also cannot be sent through the first interface or the third interface because the VLAN ID is different. But the message also can be sent to switch 2. Compare with the native VLAN of the switch 1, we will find the VLAN ID is different. The message VLAN is 20, but the native VLAN of switch 1 is 30. So the message also will be sent out carries the VLAN 20. And when switch 2 receives it, this one carries a VLAN ID, and we will directly send the message out to PC5 and delete the VLAN ID to become untag without the VLAN tag information. And then we will send the message to PC5. And the next step, if PC3 sends the message out, also is a standard Ethernet message. We will send to switch 1. Switch 1 will add the VLAN tag is 30. But pay attention about this step. This message only can be sent to switch 2, right? And the different one is the native VLAN is same with the message VLAN. So about the switch 1, when we send out the message, we will delete the VLAN. This is the VLAN 30. And when switch 2 receives it, we will find this is a standard Ethernet message without any VLAN tag. So we will add one VLAN. Which VLAN will be added? Depends on your native VLAN. About the switch 2, we add the native VLAN is 20. So we will add the VLAN 20, and then the message will be sent out to PC5 because the second interface also belongs to VLAN 20. Finally, the message will be sent out. So from the communication by left to right, we will find the result is PC1 can send the message to PC4, PC2 and PC3, all of them can send message to PC5. But we say communicate with each other means the right message to left also can be sent out. So let's see the process, how to forward the message from right one to left. And about the PC4, if we send the message out, when PC2 receive it, we will add the VLAN 10. Then the message will be sent out. Because the native VLAN is different with message VLAN, so we will carry the VLAN ID to become 10, and when switch 1 receive it, I will directly delete the VLAN tag and send to PC1. So we will find PC1 and PC4, they can communicate with each other. This is the answer of option A. And then let's say the PC5. If PC5 sends the message out, and when switch 2 receives the message, we will add the VLAN. The VLAN is 20. And about the switch 2, when we receive the message, and we will check the VLAN tag and the native VLAN ID, but we will find the native VLAN ID and message VLAN is same. So we will delete the VLAN and send out a standard Ethernet message to switch 1. And when switch 1 receive it, I will add one VLAN of our native VLAN. So finally, the message will be added of VLAN 30. And because now the message carries a VLAN 30, only the third interface can be sent out and deletes the VLAN to become 30. So finally, PC3 will receive the message. So in this process, we will find PC4 and PC1, they can communicate with each other. It's very easy to understand. But about the PC5, when PC5 sends a message out, the PC5 sends a message to PC3, we can receive it. But PC5 sends a message to PC2, we cannot. Okay, so this is the whole process of this practice. And about this practice, I only let you to understand what's the function of the native VLAN about the trunk interface. In the real network, normally we will make the same native VLAN with the two switch connect with each other. So finally, the result you can easily to understand that the same VLAN, they can communicate with each other. So about this practice, I only let you know what's the function of the native VLAN. And the next step, let's say the STP principle. Why we need the STP? Because in our LAN network, local area networks, we usually consist of multiple switches to communicate with each other, right? And in order to avoid broadcast domain, and it's necessary to ensure there is no path loop in our network. Because about the layer 2, if you have the loop, and finally the message will be sent out all the time until your network is broken. Because about the switch, we cannot avoid the broadcast domain. So how to solve this problem? One solution is we can use STP protocol. And this protocol, if we run on our network, and we can make all link into a tree without the loop. And finally, we can provide the redundant backup link, and also we can avoid the loop, right? So this is the basic function of STP. And I will show you the topology to let you know. For example, in this topology, if PC1 and PC2 within the same VLAN, but they can maybe connect with different access switch. And about the upper, we will have the distribute switch. And in this topology, if PC1 and PC2 sends a message with each other, and there is the communication link, but we will find there only one path between the PC1 and PC2. That means if one link is broken, the communication cannot work. We cannot send the message to PC2 again. So in this scenario, we hope we can have some redundant link. If one link or maybe one device is maybe if one device is broken,
we can continue to use a backup one. For example, add one link between the access switch and distribute switch. But in this topology, we will find there is a loop. So maybe some message will be sent out within the loop all the time until your bandwidth is not enough and then your network is broken. So we also hope that we can have the redundant link, but also avoid the loop. So in this scenario, we can deploy the STP. Someone maybe say what's the phenomenon, how to do the judgment that there is a loop. And we also have some phenomena of the loop. You can check. For example, about your switch port indicator flashes rapidly at the same frequency. You maybe have to check there is a loop. And the second one, if we have the loop, the MAC address table will association. That means maybe when you check your MAC address table, you will find one MAC address connect with the first interface, and the second time connect with the second interface, and come back to first interface again. So in this phenomenon, maybe there also is a loop. And the third one, the switch is running out of resources, and the logging operation is exceptional. So that means all the switch will forward the message because of the loop and send the message all the time, but finally the message cannot be sent to the correct result. And we don't have any resources to maybe to reply your management or maybe reply some other operational because we focus on forwarding the message. So this is a phenomenon. And if we have the loop, there are also some hazards. The first one, the link will be broken, right? And the host system response is slowly because we receive so many messages from the network, but the message is saved. The layer 2 switch are slowly to manage because we need lots of resources to maybe reply or maybe to forward the broadcast message. The third one, we also have the impact on the CPU of the gateway devices because some gateway devices also will receive the message from your loop network. So there are some hazards maybe happened when we have the loop. And then let's see the process, and I will show you an example what's the result of the loop. It's very easy about this topology. We have three switches, switch 1, 2, and 3, and there is a loop, right? We directly connect with each other, and here two pieces, PC1 and PC2, and all of them belong to the same VLAN of the VLAN 10. And about the switch, we have the MAC address table, right? About the MAC address table, we will learn some MAC address to record, add into the table, and then forward the message according to the MAC address table. So if now PC1 and PC2 have to forward the message with each other, and let's say the process if there is a loop. The first one, within a VLAN, if some unknown unicast message, we will flood it to all ports except the receiving port. So this is a basic principle of the layer 2 switch. If you forgot this one, maybe you can go back to see the video of layer 2 switch principle. And the second one, the switch is based on working principles. The first is learning records. When we get the message from the terminal, I will add the source MAC address and into the MAC address table. Also will connect with some interface. This is the first principle of the switch, learning record. The second one, we will look up the MAC address table and finally decide to forward the message or discard the message or maybe flood the message. So this is the second one. So this is a basic principle of layer 2 switch, right? And at the beginning, if we start the devices now, the MAC address table is empty. And the next step is
if PC1 sends out the message, the source MAC address is PC1, the destination MAC address is PC2. If switch 1 first time to receive the message and our MAC address table is empty, so about this unicast message we call is unknown unicast message. And switch 1 receive it, first action is learning. We will add the source MAC address and the receiving interface and the VLAN add into the MAC address table. So you will find about the switch 1 MAC address. We will add the VLAN 10, the MAC address is PC1 MAC address, and the interface is gigabit 0/3. And then we have to flag the message, right? Because this is unknown message, unknown unicast message. When we take the destination MAC address, PC2 MAC address to match my MAC address table, we cannot search the information. So this one's action is flagged. I will send a message to gigabit /01 and also the /02 and also the fourth interface of switch 1. So about the switch 2, we will receive the message, right? And when we receive, we also will learning the MAC address, and the second action is flag the message. So we will add the source MAC address of PC1 into our MAC address table. The same process of switch 3, we will add the MAC address 1 and also record the VLAN 10. And the receiving interface is gigabit 0/1. So this is the action of the switch 1 and switch 2 and switch 3. Of course, in this scenario, PC2 already receives a message from switch 1. So the correct step is we can stop here because PC2 already receives a message from PC1. But in action, actually, we will continue the next step. About the switch 2, because this is unknown unicast message for switch 2. So when we're learning the MAC address later, I also will flag. The flag result is I will send the message to switch 3. Switch 3 also will do the same process, learning the MAC address from the message and finally flag to switch 2. Okay, then the result is because now switch 2 and switch 3 already received the message from the other side. So switch 2 will find now maybe the MAC address of PC1 already connect with switch 3. So we will update the entry of my MAC address table. I will delete the PC1 MAC address, connect with the first interface, and change to become connect with the second interface. The same result with switch 3. I will delete the original MAC address entry and add a new one, right? And then when we update the MAC address table, I also have to send the message out because the destination MAC address is PC2. I cannot find on my MAC address table. This action should be flagged. I will send the message to switch 1 because I received the message from switch 3. And when the switch 1 receives a message from switch 2, I also will update my MAC address table because about the original one, I received the message from PC1. But now I receive the same MAC address from switch 2, so I have to do update. This is the association with switch 2, switch 3, and switch 1. But pay attention about the switch 3. I also received the message from switch 2, so I will flag the message to switch 1 again. And when switch 1 receives it, I will delete the original message from switch 2, add a new one from switch 3. And finally, about the switch 1. I receive the message from 2 and 3, and I will flood it. Flood to switch 3 or maybe flood to switch 2. Depends on which message received from switch 2 or switch 3. And also I will broadcast to PC1 and PC2. And you will find the message will be all the time to forwarded between switch 1, switch 2, and switch 3. And the PC1 and the PC2 will receive lots of same message from switch 1. So there is a loop. Right? The switch 2 and switch 3 also will update the MAC address table again all the time. 1, 2, 1, 2, and 1, 2. So this is a circle. The broadcast stop in the network and repeated the data frame will be flooding within the switches. And one circle, there may be one more message until the bandwidth is not enough, and we will stop here. And in this scenario, because we use lots of bandwidth to forward the broadcast message, the other correct message cannot be sent out because the resources is not enough. So how to avoid the loop? We can deploy the spanning tree protocol STP on switch. And in this scenario, if we use a protocol, we can logically blocking loop interface. For example, here we can make the link to become logically down. Logically down means when you check the lighter, the color also is green, but the interface will not forward the message again. Until some active link is broken, we will make the logical blocking interface to become up again to continue forward the message. So in this scenario, we also can provide the redundant link but avoid the loop. What kind of protocol of STP? The basic function we already talked before, we can avoid the loop and also can provide some redundant backup function. Like the topology, Z is a loop, and logically we will block the interface. But pay attention, the blocking not means you have to delete the link. The link still is connected with the switch, and the lighter also is green. The physical layer status will become the up, and the layer 2 status also will become up, but the interface will not forward the message again. Until the physical interface, the active link interface is disconnected. Maybe there's some broken, right? And then we will activate the block link again to help us forward the message and provide the backup link. So this is the function of the STP. And about the spanning tree, we also have lots of classification. We can have the STP, ISTP, and MSTP. 3 types of STP. And in different vendor, maybe some private protocol of the STP depends on the requirement. And about the RCNA course, we only focus on the STP. And about this protocol is the protocol is organized by the IEEE organization. And we have different detailed protocol indicate different type of STP. About the STP, the IEEE 802.3D, ISTP is 802.3W, and MSTP is 802.3S. And later we will talk about the detail of the STP, how to work, which interface can be blocking, and if the interface, the active interface is down, how to make the blocking interface up again. And this is a basic function of the STP.
And of course, in the STP, we have lots of disadvantage. That's why we will have a new version of RSTP and maybe better version of the MSTP. So we have different clarification about the STP. So this is the first one. Why we use the STP? If we don't have this protocol in our network, maybe there is a loop. And what's the hazards? We have the one example to explain the hazards, right? And the next step, next video, we will talk about the detail. How to work about the STP.